All right, so let's look at the process of stuff dissolving in solvents. So if I put my spoonful of sugar in water, what is happening? Well, on a molecular or atomic level, right, you've got the solvent. Let's say our solvent is water, right? You've got the interactions between the water molecules. I guess I should draw them. What would those primarily be in water molecules? Exactly. Oh no, hydrogen bonds, right? So I'd have my hydrogen bonding, my relatively strong hydrogen bonding interactions between those water molecules, holding them together. The solute, and if this was sodium chloride, I have the electrostatic attraction between the sodium ions and the chloride ions, right? And we can use Coulomb's law to predict the lattice energy, the strength to which they're holding onto each other, right? The bigger the charge, the stronger the interaction. The smaller the atomic or the ionic radii, the stronger the attraction. Okay, so you have some interaction here, right? These guys are holding on to each other to some degree. In order for them to become a solution, we have to disrupt those interactions, and then we get some stabilization back if they can interact with each other. So with sodium, we already drew this picture. Here I have chloride. How is that going to interact with water? Well, it's going to interact with a partial positive on the protons, or the hydrogen atoms in water, right? So you get the partial positive interacting with the negative charge, right? And that'll surround it all. The sodium ions are the reverse, right? They want to interact with the partial negative charge on the O, right? They interact with the lone pairs on O. And those interactions between chloride and the hydrogens, or sodium and the oxygen atoms, is the energy or the stabilization associated with that. So these are the two things we have to consider. How stable is a solvent, or how stable are the solvent and the solute by themselves? How stable are they when they're together? And to look at them, we can think about, well, hydration energy is what we're talking about here, right? This process is called solvation or hydration. If your solvent is water, it's called hydration. Any other solvent would be called solvation. If we can basically think of these processes as endothermic or exothermic processes. So remember, in an energy diagram, low on the energy diagram means stable, right? Higher means less stable. So remember what we're doing here. We're starting here and here, right? If these guys are really stable here, right, and when they mix, they're less stable, that would be an endothermic process, and we wouldn't expect that to happen, right? If it's more stable as the solids, we wouldn't expect it to want to become a solution very much. But if the reverse was true, where the starting materials were less stable than the combined mixture, that would be an exothermic process, and that is a favorable process. So we can think about this that way, and we see a lot of that. So if I dissolve acid in water, right, what I get is protons, chloride ions, solvated by water. That's actually an exothermic process. If I'm holding that flask, right, and wearing my safety glasses, I'll feel the flask get warm as heat is released in that exothermic process. Hydration, we said, right, is the process in which ions surround water molecules, and they are arranged in a specific manner. Positively charged ions interact with a partial negative charge on O. The negatively charged ions interact with a partial positive charge on H's, right? So in the solvation process, remember, so we have sodium chloride with its electrostatic attractions between its ions, right? We think about that energy or stability, and we compare that to the solvated sodium ions and chloride ions, and compare that stability to the other to decide if it's going to be favorable or unfavorable. We need to recognize some solubility rules. We should be able to look at salts, ionic compounds, and predict whether they're going to be soluble or not. And there's a couple of rules. All right, more memorization, which is good for you. So if you have a compound, right, the way you read this thing is, if you have a compound and it has any of these guys, with a couple exceptions, then it is soluble. Right, so if I have a salt with lithium, sodium, potassium, rubidium, cesium, or ammonium, or nitrate, or bicarbonate, or chlorate, then it will be soluble. So it doesn't matter what it is. So sodium iodide, as soon as I have sodium, it will be soluble. Ammonium, right, acetate, right, as soon as I have ammonium, it's soluble. I don't need to worry about the other guy. Halides, like chloride, bromide, iodide, and sulfates, are usually soluble, with exceptions. So the halides have three exceptions, right? They are soluble except in the case of silver halides, bromides, and silver iodides. So the chloride, bromide, and iodide of silver is insoluble. They'll be solid in water. So silvers, mercury, and lead are the three exceptions to the solubility of halides. Sulfates are the same. They have 6 exceptions, though. But they don't really count as 6 because 3 are the same as the original ones. And so what you have is silver, mercury, and lead, and calcium, strontium, and barium. These guys are next to or below each other on the periodic table, so they're easy to find too, right? Calcium, strontium, barium, find them on the periodic table. And remember that they, when they combine with halides like chlorides, bromides, and iodides, form solids. They are insoluble. So these guys are either always soluble when they're part of a compound, ionic compound, or usually soluble with 3 or 6 exceptions. The mostly insoluble guys, so if you have these guys, carbonates, phosphates, chromates, sulfides, hydroxides, and oxides, you are insoluble with the exception of the things that are always soluble to start with, right? So alkali metals, we already said, are always soluble. Ammonium ions are always soluble. So if you combine any of the alkali metals or ammonium with any of these guys, it'll still be soluble. But everybody else is insoluble. There's kind of one exception for hydroxides and oxides, is that the barium ion is soluble. So barium hydroxide is soluble, whereas almost all other hydroxides are insoluble. Calcium hydroxide is slightly soluble. All right, so let's practice this. So try to use these rules to predict whether the compounds on the bottom here are soluble or insoluble. So just take a moment and think about magnesium chloride. All right, the way I would look at this is, so there's no rule about magnesiums, but there is a rule about chlorides. Halides are usually soluble, right? So it will be soluble unless it's one of 3 exceptions: silver, mercury, or lead. This is not one of those exceptions, so it will be soluble. Ammonium chloride, ammonium salts are always soluble. Done. All right, it doesn't matter what chloride would be. Potassium hydroxide. So even though hydroxides are usually insoluble, potassium, right, the alkali metals, are always, or ions of the alkali metals in compounds are always soluble. Cobalt, we don't know anything about, right? We have no rules for transition metals, but nitrates we do. These are one of the always soluble things. So nitrates, ammonium ion, and the alkali metals, ions of the alkali metals, are always soluble. Silver we don't know, but chlorides, halides are usually soluble with 3 exceptions: silver chloride, mercury chloride, and lead chloride. So this one is insoluble. Carbonates are usually insoluble. The only exceptions would be if this was a sodium, right, alkali metal, or ammonium, and it's not, so insoluble. Calcium sulfate. Sulfates are usually soluble. My thing's getting them WMS, I'm sorry. Usually soluble with 6 exceptions: silver, mercury, lead, calcium, strontium, and barium. So this guy is insoluble. All right, have a think on that. We need to be able to recognize soluble and insoluble salts using these solubility rules. Another thing we want to consider is the solubility of liquids in each other. And basically what we say is like dissolves like, which means polar things dissolve polar things, non-polar things dissolve non-polar things, but non-polar things don't like to mix with polar things. And this is what we're seeing here. So hexane, right, is C6H14. Water we know is H2O, and carbon tetrachloride, well, CCl4. Are these polar, or what are the primary intermolecular interactions between these guys? Well, water's easy. We know that's a hydrogen bonder, right? He's polar, hydrogen bonder. If you're only made of C's and H's, right, or you have symmetry, in this case, this guy's only C's and H's, he's non-polar. The primary intermolecular interactions will be London dispersion forces. CCl4 is not made of only C's and H's, but you have a central C with 3 chlorines around it, symmetry, right? If everything around the central atom is the same, it's non-polar. It's got to be non-polar, LDF. And so polar water doesn't want to dissolve nonpolar hexane, and it doesn't mix with nonpolar carbon tetrachloride. Now, well, I guess one question is, why is the hexane on top and the carbon tetrachloride on the bottom? Well, it has to do with density. Carbon tetrachloride has a higher density, and so it'll be on the bottom. Hexane has a lower density, it'll be on the top. What would happen if I got the water out of there? What would happen with hexane and carbon tetrachloride if they saw each other? They would mix. They would be what we call miscible in each other. If you're soluble in all concentrations, you are miscible. Oh, that didn't work. Let's see. All right, another classic, right? It mixes as well as oil and water. Oil is nonpolar, water is polar, and so they don't mix. They are immiscible. This is a B-52 shooter, but sort of unrelated to what we're talking about, tragically. Everything there is soluble in water, but what we're seeing here is just different densities. Right, so if you take a half-ounce Kahlua coffee liqueur, a half-ounce Bailey's Irish Cream, and a half-ounce Grand Marnier orange liqueur with a little Bacardi 150 one on top for the fire, right? You can mix them up carefully because their densities are different enough. And if you pour them carefully on each other, you can separate them that way. But they are miscible. If you stirred that up, it would be an unattractive mess. Let's see. Okay, let's predict then. So predict if these are going to be soluble in each other. So what we're doing is we're deciding, are they polar or non-polar, right? If they're both polar, they'll be miscible. If they're both non-polar, they'll be immiscible. Okay, you can do this yourself. Pause me and turn me back on when you're ready to go over them. All right, I guess I'm back. So symmetry, non-polar. Only C's and H's, non-polar. Both London dispersion forces, so these guys are miscible. Sodium chloride, this one's interesting. So it can form sodium ions and chloride ions. In terms of polarity, charged things are the most polar. So they want a polar solvent. Water's polar, ammonia is polar. So these guys are miscible. What about this guy? Here we have, so this is ethanol. So you have a portion of C's and H's and then an OH, right? This is a hydrogen bonding group. So it's polar, but this part is non-polar. So what you have is a non-polar region and a polar region, okay? And it turns out that the polar region is important enough that in water it's soluble, so it's miscible. Here, though, C4H9 in water, what's happening now? So if I drew this out as a condensed structure, we would see this. So now instead of just having 2 carbons and a polar hydroxyl group, we have 4 carbons and a hydroxyl group. We have a longer non-polar region. This guy is soluble. This one, it's getting less and less soluble. So how would we know that? Well, I don't think we can. What it is, it's getting to be less soluble in water. Some of it still dissolves, but some of it doesn't now. All right. What would happen if I went to C5H11OH? Right, should be even less soluble. Okay, so you don't have to memorize this, but just understand that if there is a non-polar region and a polar region, sometimes they can compete. Finally, we have this guy, C5H12. This is pentane in water, 5 carbons in a row, and so water's polar. Pentane is a London dispersion force interactor and non-polar, so these guys are immiscible. All right, so how do you recognize non-polarity, non-polar things? They're hydrocarbons, right, made of only C's and H's. There's symmetry. Everything is the same around the central atom, right? And if they have London dispersion forces, which are testing for those same properties, they're non-polar. Polar and charged things, right? So we're looking for dipole-dipole interactors, charged ions, and hydrogen bonds. So CH4 is non-polar, right? Central carbon with 4 hydrogens, all the same, non-polar, London dispersion. Carbon tetrachloride, central carbon with 4 chlorines, all the same, non-polar, London dispersion. But these 3 in the middle, right? I have 1, 2, or 3 chlorines, which are making them different. They're not all the same, so these guys are all polar. They'd be dipole-dipole interactors. Right. This is why it's tricky to be a polar bear. We'll look at gases in solution next, the solubility and properties of gases.